And just like that, we're down to the last 3 days, 23, 24, and 25 today. And we've got a LAN party. Do LAN parties still happen? Is that still a thing? Just have this image in my head of people lugging CRT monitors around. So there's a network map for the connection between two computers. Oh, actually, that's kind of funny. I wonder how many people doing this year don't know what a LAN party is. I guess for those that don't, it's basically like bring your computer to your friend's house and then everybody hooks up via Ethernet cable between their computers. So we get puzzle input. These are connections between computers then. Each line of text in the networks represents a single connection. KHTC. Connections aren't directional. This is starting to sound like a good day, maybe for Petcraft. We'll see what actually happens. LAN parties, multiplayer games. Which one? What do we need to locate? It says locate it. Oh, posters for a LAN party. Okay, we need to find the LAN party. We need to find the LAN party by finding groups of connected computers. Okay, I don't. Start by looking for sets of 3 computers where each computer in the set is connected to the other 2 computers. So, like, we could dump this into probably pretty much anything, but we could dump this into PetGraph, do strongly connected components or something like that. Actually, if we dump this into PetGraph and we build those connections as we go, then we end up with a graph and we end up with a bunch of these. Find all sets of 3 internet-connected computers. How many contain at least one computer with a name that starts with T? I guess we're guaranteed to only have sets of 3 interconnected computers. So I feel like the only thing that would be weird is if there's like a duplicate name, but I feel like that wouldn't work. KHTC, QPKH, KHUB, KHTA. Wait, so KHTA, UB, TC, and QP are all connected? Oh, okay. So we're supposed to. There are computers that are connected to more. This. Wait, what? What about KH and TA? Right, KHTC, KHQP, KHUB. So TC, QP, UB, and then TA. KHQ, QP, UB, and where's TC? Why is this 3? Okay, so we need nodes that have connections to both other nodes, right? So KHUB would require UB other thing, KH other thing, and they would both need to be the same other thing. I feel like I want to put this in PetGraph just to visualize it. So maybe we start with that, even though we probably don't need it for right now. I'm trying to think of what data structure would just make this easy for us. So we could iterate over the graph in various ways, but in terms of implementation, I don't think the graph gets us very much. Let's just create day 23. Like the graph would get us a really nice visualization, which I really like. And I may do the pet graph anyway for that visualization because it will help me think about it. But we have groups of computers, and I guess technically we're looking for all the cycles, right? So one thing that's really nice about PetGraph is it has kind of an ecosystem built on top of it. There are other crates that build on top of the PetGraph data structure. This seems to find cycles based on, I guess, Johnson's algorithm, and it has a link to, or not a link to, but it references a paper. I like the idea of just playing with this. I like the idea of visualizing it. Let's see, PetGraph 0.6. I think that's fine. So PetGraph path or graph cycles day 23. I'm kind of choosing to do this in a little bit more of a heavyweight way because I have a feeling that those cycles are going to become important later, which is just kind of a hunch. It may not actually be important at all, but this is quite literally what we need, right? So we're going to pull this stuff in. We're going to drop this up here. We're not going to assert anything, just work day 23, part 1. What are we doing here? Oh, right. We didn't return anything here. So let me return some like random string. That's not how you return a random string. And what was the actual thing that we need to, how many contain at least one computer with a name that starts with T? So we need to get the groups of 3 computers, the like cycles, and also check the node names, which is 7. So the answer to processing this is going to be 7. Now our test fails, which is great. This is not that tough of a parser, but I do like having a parser. So we'll do a result and a vec of tuples of string slices. And I missed a character. So separated list 1, line ending, as we've seen before. And then separated pair, alpha 1, tag dash, alpha 1, input on the end, we have a parser. I feel like at this point, we've basically covered all of this. So that gives us this, which is great because then we can do input edges equals parse input. And I know we usually use Miet here, but you can also just unwrap it. It's not a big deal. It will crash your program, right? So we could also do into diagnostic here, and that would also work, which is much shorter than what we've been doing. I just tend to customize the thing. So this then needs edges, and we have our graph. The trait from string slice is not implemented for node index. So this is kind of like using node indices, which we don't really have. We have node weights. So we could do graph map, but ungraph map is actually what we want because ungraph map is undirected graph map. Now the question becomes, does this expect anything in particular? I think because we do ungraph map there, then we have to do g dot into graph here to get the cycles. Oh, this is interesting. It wanted a couple more, types and stuff, and we end up with borrowed data escapes outside of function. So we call the lifetime of this reference input 1. Input is a reference that is only valid in the function body. So visit all cycles must be doing something funky. Oh no, into diagnostic is probably actually the issue here. Yeah, that was actually the issue. So the issue actually was that the result type or the error type for NOM actually contains the input, and the input we're using as a reference. So then we are kind of packing that into the error type if we do into diagnostic and returning it. So long story short, if we map over it and we create a new string from that error string, then it works. So now we have this. It looks like we have quite a few cycles here, actually. Let's see if we can do, right, this is indices. So then we can print out just the groups of 3. Interestingly, this does give us duplicates. So we get 9, 11, 15, and 9, 15, 11. But of course, what I wanted to do in the first place was visualize this. That's why we put it into petgraph in the first place, not to use that random crate that we found, but rather to use this. So dot comes in with petgraph. I guess we're calling this G. We could call it whatever we want. We're not using input, so let's underscore that. And let's just work, and we should get this. And we can actually just view that right inside of VS Code if we do graph viz toggle preview. So it looks like this is our graph, which is really interesting. So everything is connected. Nothing's actually separate. This is our list right here. The only problem with doing it this way is both A, there's no dark mode, and B, if I hit plus, then everything gets bigger. So CODETA, where's CO? CODETA. That is a valid cycle, and COKATA is a cycle. DEKATA is a cycle. QPTDWH is a cycle. TBVCWQ is a cycle. So I think we're looking pretty good here in general, in terms of at least, getting a graph, seeing what it looks like. Now, I don't know what cycles is supposed to be over here. So hopefully cycles is just like something usable, maybe. That would be cool. No, cycles is just all of the nodes. So actually this doesn't seem necessary because it seems like all of the cycles are already here, right? So we'll indices.iter.map, collect into a vec, and now we have all these lists. Now this iterates in both directions, so it's a little bit weird for what we actually want. And I know we didn't actually look at this crate at all. So it has this trait called cycles, which has visit cycles, and visit all cycles. Visit cycles applies a visitor to each cycle until we're told to stop. Otherwise, we find all cycles. So maybe this will end up being useful for us, but I don't think right now it actually is. We have cycles here. So we want cycles.iter.map cycle, or I guess filter, right? Cycle.length equals 3. And then we map this into graph node weight by index, right? So this is cycle.iter. I guess this is the whole thing, right? We already know what this is going to be. And we just drop this in as a vec. And this is not indices, this is cycle. And if we debug cycles, that is not what we want. We want to debug output. And we get a whole bunch of stuff. And we want to make sure that we don't do like UBVCWQ. So we do have the two things here. Interestingly, these are all sum. I think that's because of this. So I want to unwrap this, and we'll just say sorted to sort everything. And then we'll dot unique here. And this is like probably overkill in terms of like the amount of different stuff that we are doing to get this list, but it was not costly for us overall. So I'm not too worried about it, right? There's a way to prototype with existing stuff and then drop that existing stuff when it no longer works and come with something that is a little bit more specialized. So this should give us too many answers because we aren't filtering for those nodes yet, right? So 712. And here we're expecting what? We map here, sorted uniqued, and then we can just filter here. And then we'll iter.map isn't what I want. .iter.any node, right? Node weight includes, contains T. And then our test passes. So we're doing the right thing here. Day 23, bin part 1. Run this in release mode because why wouldn't we? No idea how long this is going to take. We're doing all of the cycles for everything, and that might be an issue. Didn't take a look at the actual input at all. Have no idea how long this is. The answer is extremely long, by the way. 3,381. Okay, we can actually end up seeing this graph at some point. It's really interesting to see how long this takes. So in the meantime, if that's even going to be capable of running, let's toggle a preview here. There's a lot of nodes, so it might take a second. So this is taking like ages. And offhand, I don't really know how long something like this should take. We did get a visualization of our graph. So in the meantime, I want to get that image that we generated. So day 23, did I put that in source? I did. Why not? Let's just do this in source. What else do we have going on in source? Nothing. Apparently I don't have GraphViz installed currently. So let's take a second to brew install GraphViz. The downside of having done that is that Homebrew is now going to take forever to, I don't know, upgrade everything on my computer. Sometimes that's just not what I want to do, Homebrew. But I do think the unfortunate thing in our attempt to use this other crate is that it is finding all cycles in general. And what we really need is limited cycles, right? We only need cycles of size 3, which would speed this up quite a bit because then we wouldn't need to find all cycles. The code for this is on GitHub. It's about 250 lines. They have a cycle finder vec with a graph and strongly connected components as a vec. I feel like one of the things we could do is do a bunch of smaller graphs, right? We don't need to do this giant everything's in one graph approach. We could do a bunch of smaller graphs that we build from that first graph. So we build up the first graph, right? And then for every node, we take it and the nodes next to it and basically copy that out as a separate graph. And yes, that would mean we do that, 4,000 times in this case, potentially. Actually, that's not the number of nodes. This is the number of edges. And I forget how big, that's not even the right day, right? Input part 1, we get 3,300 edges, but it does seem like that would be potentially simpler. And then we could run this as is on that, which would be able to work quickly. And we would also be able to show some progress in between. I'm kind of looking at this algorithm that they've implemented for finding the cycles because it does work to find the cycles. I think there are a couple of things that we could make as hard-coded improvements that you can't do in the general case, such as limit the size of the cycle. So this is effectively the cycle finding algorithm. And that is for every node in the strongly connected components. So for us, it's going to be the entire graph. Then for every, I don't know what self.b is, but we can look at it. Self.circuit, what does circuit do? Circuit is a stack that we push a specific node from the strongly connected components onto. We set it blocked. We check the adjacent vertices and so on and so forth. I don't know exactly what they mean by blocked and unblocked, but I can take a hazard of guess. Okay, I'm going to stop this from running. It's clearly not going to finish in any reasonable amount of time. I let it run for 18 minutes. Sick. So I'm just running graph dot output into a PNG. Don't know how long this is going to take, but this is going to be the big graph, not the smaller graphs that we've been talking about. Graph is too large for Cairo render bitmaps. Scaling by to fit. Okay, that's not good. That is very not good. There's got to be a better layout algorithm for this. So it does feel like we can't really do much worse than we just did. So let's get rid of the dot config. So one thing we can do right now is probably just use neighbors to then build up this new graph, this subgraph, whatever you want to call it. But I have an inkling that we're going to have to do more than just 3 in the second one. So I'm taking a second to kind of make sure that we can, or try to make sure that we can actually expand this to, I don't know, 5, 7, 52. I don't know how many circles are going to be needed, or circular. Obviously, if that happens, I don't think we'll be able to use our current approach. But I think this idea of making smaller groups of stuff is going to help. So if we have edges, that's going to be a tuple of everything. I probably want also, well, we actually don't need a list because we'll already have a list, right? G.nodes gives us a nodes list. So let's get rid of what we have here, or at least comment it out. We didn't use some of this stuff, so we'll delete some of it. And we currently have not found in this scope for output, which is totally fine. We aren't logging the node. So in this case, each node has a set of neighbors. In this case, it almost looks like they all have 4 neighbors, which is really interesting. So if we have node and neighbors, then really all we need to do is check to see if KH and TC share a node. So right, we've got KHTC, KHQP, KHUB, KHTA. So really the only question is, do any of these neighbors connect to each other? So maybe we g.neighbors.node.collect for the moment, because we've got the root node we're processing. We've got each of its neighbors. I feel like this is all of the nodes that can be involved. So we have root node, we have the neighbors of root node. We need for each neighbor to check to see if it's connected to root node. So g.contains edge, node and neighbor? No. Yeah. No, node and neighbor contain an edge because we just did that. We need to know if any neighbors contain edges. So we get like AB in g.neighbors.tuple combinations, and G contains edge AB. And in that case, then this is filter. Filter AB, this code goes into filter. It has to contain the edge and node AB.any and n.starts with, or no, not starts with, contains T. And I have severely messed with Rust Analyzer somehow. I fear I am missing a bracket. I am missing a paren here. Okay, so basically for node and g.nodes, we check to see if the neighbors of the current node contain an edge between them, and node A, B, any of them contain T. Now, this is fine, except I believe that if we now go to any of the other nodes, we'll duplicate the work for the original. So we'll still need to actually keep these and unique it. So I think we actually turn this into a filter map, and we then sum with like node A, B as an array. And really we want this to be sorted. So we'll return a vec here, I guess. I feel like we shouldn't need to do that, right? Because this can just be a function if we use, there's then and then there's then and then there's then and then some. Then lets us use a function. So if we do let nodes equals this is mute.sort, and we return nodes. So we're getting sorted nodes here. And I guess we aren't using the result of this, right? And we're not collecting it either. So for every root node, we want to go through the neighbors. We want to see if the neighbors contain edges between themselves. We want to make sure that those neighbors contain some kind of T in them. And then we want to return a sorted version of those nodes so that we can unique them later. So I think this is g.nodes.map node, right? Get our number of braces correct. And then this is the g.neighbors call here. So maybe we flat map here, and then we .unique.count. This is output. Flat map has a problem for some reason. Cannot be called on flat map. Unit is not an iterator. That seems fine to me. Unit is not an iterator. We need to remove that semicolon. We get some may outlived borrowed value node. I think we've solved this in past videos, right? We would have to move these in, but if we do that and we say this closure captures by moving, then that's a move out of G for some reason. Why? I'm not exactly sure because it's a string slice. I guess it's not a reference to a string slice, so it's not a reference to the node, it's the node itself, which would make sense. So we're getting whatever we use as that node weight as, what could be considered an owned value rather than a reference to it living there. So the easier option, the more straightforward way to do this is to collect this into a vec, and then we don't have any problem at all. If we work with owned values, then we can pass around the owned values. And the issue is actually that we were capturing G, right? We're capturing G out here. We use G.nodes here, G.neighbors here, and then G.contains edge inside of the closure that we were then moving. So that's fine. Another option is to add a shared reference up here. So if we add a shared reference here, then this is a shared reference to the graph in G, right? If we check the types. And then the shared reference can be used across all of these invocations because we're, not mutating the graph at all. And thus we can share this for as long as we need to because G.nodes, G.neighbors, G.contains edge, all of that is like shared reference usage. So it doesn't matter how many times we use it. It doesn't matter how long those live for in this context, etc. So you can either do that collect, which will create a new vec solving the problem, or there are other solutions as well, such as passing in a shared reference if you're not doing any mutation and things like that, right? So down here we have a shared reference now. If we remove that, then this becomes that owned graph map type. And that's when we start to run into issues where it's like, hey, you need to, clone this because we're moving it out there. But with the shared reference, we are not doing that. So we end up with this output value. This is no longer going to be output.length. This is just output. And we get some Clippy warnings, which is fine, but our tests are passing. And our test passing is really what I'm interested in. And look how fast that ran, 2544. 2544 is not the right answer. It's too high, which is interesting. Oh, right, because we are filtering out the... Okay, let's do inspect. Let's keep the number we had here. 20, this is too high. We inspect, we get the value. This value I am going to debug. And this should be a unique set of all the values. This unfortunately does work for the test. So that's really unfortunate. Let's make the test fail. And we end up with 1, 2, 3, 4, 5, 6. I think we're also doing some debugs up here still. No, apparently we're not. Where's node? There's node. Okay, so we get 1, 2, 3, 4, 5, 6, 7. Let's change this out for info, and we will change this out for test log test. And then we end up with dumping too much stuff in here because I always forget to skip the input. So we end up with the additional context. And now we get this list of stuff, which is a little bit easier to read. So let's take a look at what we're supposed to get. Only consider sets of 3 where at least one computer's name starts with T. Okay, I was right with starts with. I think we only have starts with values in the test input, so that's why I didn't catch it. But it's not contains, it starts with, which will give us the same value, unfortunately, for our test. So our test should still pass. And then our cargo run here should give us a significantly lower value. We should be able to put that in, get the answer. Yeah, gold star. Before we look at the terrifying part 2, let's take a look at the Clippy lint here, and let's explain what we actually did. So we have these connected elements, right? And we've looked at the preview here. In this case, we're looking at the preview for the whole actual real input. So it looks significantly more complicated, and there's quite a bit going side to side. At the end of the day, we end up with a bunch of nodes. They have a bunch of connections. We're looking in the first part for any connection that is 3 nodes that are all interconnected, and one of them starts with T. So this is TK right here. And this one draws a line up to QL, which draws a line over to VY, which draws a line back to TK. And this dot visualization makes it pretty easy for us to like double check to make sure that we're looking at things that are actually connected, et cetera, et cetera. Now this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like 13 connections out from it. So that is quite a lot, but our test input is quite a bit smaller. So I think we actually have our test input here. Yeah, this was the test input. So let's toggle the preview for that. And this is our test input preview. So quite a bit smaller, quite a bit more understandable, but same idea. So like TA, CO, KA, TA, right? TA, CO, KA, TA. This would work, and so on and so forth for all of these. The algorithm we tried to use from that crate works on this graph. it does not work on that really massive graph. And it's kind of understandable because if we look at that crate, it's worth noting that this is like a 0.1.0. So like somebody put this up as a demo at one point. It's using petgraph 0.6, so it works. And we proved that it does actually do the job. We have a link to the paper, which is also useful. And we could do performance work on the actual implementation or use the paper to implement that ourselves. But fundamentally, one of the issues I think here is that the graph is just so large, it takes a long time to process. So could we, for our real input, make that algorithm work fast enough to detect all the cycles? Maybe. We would need to do some pruning. So the crate that we were using detects all cycles, right? Any cycles. That's quite a lot. That's any of the nodes. So we've got 3,000 nodes here. We could have a 3,000 node cycle, but we only need 3. We only need cycles of 3. So we could do a significant trimming of the amount of computational processing happening there. Those are all options to us. I do think it was still useful to, check out, use. It did give us the answer for part 1, and we were able to use it to, play with some things, figure out how this works out, figure out how many cycles there actually are. It showed us that there were cycles that were bigger than 3 for sure. It also showed us that we would probably have duplicate cycles, so like ABC and ACB. But all that aside, we parsed our stuff into a group of edges, so a vec of tuples. We built an undirected graph map with node weights that were string slices from those edges, which gives us G. We take all of the nodes in the graph, flat map over them, so we're going to build a nested structure and then break it back down. We check all the neighbors for the nodes, we put those together in tuple combinations, filter map over them, so we have a root node, and then we have 2 neighbors. If those neighbors are connected, there's a 3-node cycle. So that's what this contains edges is, or contains edges. If A and B are connected, which is the 2 neighbors, then root A and B are all connected. Then we check to see if any of the nodes start with the letter T, and if they do, then this is a valid loop for our purposes. We construct an array with the sorted nodes so that we can do this unique after we break down this vec structure. Here we're also inspecting, but we don't really need to do that. And then we count the number that come out of this unique. And if we bench that, we're looking at 2 milliseconds. So fastest, probably not, but also not the slowest. So when we run this, we actually end up with some Clippy warnings. There's one in particular that I want to look at. So let's get rid of a bunch of these. We're not using that graph cycle stuff anymore. We happen to not be using dot at the moment. I want to keep tracing around, but we can always bring it back in. So it's not a big deal. So let's run this again. We don't want to check everything. So if we cargo check P day 23, it works out. If we cargo Clippy day 23, we end up with this extra warning here. Actually, is this 2? No, this is a single warning. So usage of bool then in filter map. So that is accurate. We are using .then inside of filter map. This wants us to use filter then map instead. So filter on this, and it looks like it wants us to map on the entire filter. I think that works for us. So in this case, it's going to be filter on this, and then instead of .then, we're going to do .map, and this is AB. We can get rid of a couple of these parens here now. What is the current issue with this? Move issue. So we throw move on that. I think we still need move here. So we end up with g.neighbors, tuple combinations, filter for this condition, then map to create the sorted array. And now if we Clippy, it works. Now if we bench, it shouldn't change anything. We still get about 2 milliseconds. So I'm fine with that as a refactor. Seems a little bit easier to read, honestly, filter and then map. So I'm going to commit day 23, part 1. And let's take a look at what we need to do for part 2. There are still way too many results to go through them all. You'll have to find the LAN party another way to go there yourself. Since it doesn't seem like any employees are around, you figure they must all be at the LAN party. If that's true, the LAN party will be the largest set of computers that are all connected to each other. That is, for each computer at the LAN party, that computer will have a connection to every other computer at the LAN party. Every other computer? Eee. For example, the largest set of computers that are all connected to each other is made up of C, O, D, E, K, A, and T, A. Each computer in the set has a connection to every other computer in the set. The LAN party posters say that the password to get into the LAN party is the name of every computer at the LAN party, sorted alphabetically, then joined together with commas. What is the password? So we want the largest cycle, the largest cluster, I guess. I feel like we did this last year. What did we do last year for this? I don't know. I feel like there was a graph one last year. I took a look. I couldn't find it. So I want to, what do I want to do? Let's start with taking our code into part 2. Let's delete some of this other stuff that we were using before. Let's do something silly to get some debug values out here, to do some introspection on what's going on. We're going to collect this into a vec, but this is going to be g.neighbors.count. So we end up with something silly here, right? Debug output cargo run p day 23 part 2 release. Hunches pay off. So every single node is connected to 13 other nodes, every single one of them. I don't know what to do with that information. It's obviously not as easy as picking like the node with 14. Do we take another look at the image that we produced earlier? Let me graph. Oh, we generated this for, no, the graph I think is still the old one. Yeah. Graph is still the old one. So let's reveal this in Finder and get this into some kind of a visible scenario and just scan through it. So everything has 13, right? So what is that? Why is that down there and connected to something else? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 here and then one, I think one that's connected, right? What is this line going to? That's going to this one. So this one's also connected outside. So that's 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, there's 13 in this cluster as well. I am going to kind of assume that that's true in general. This one looks kind of wonky. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Looks like we have clusters of 13 all over the place. I feel like I would want to condense each of those if I could. What is the actual thing we're looking for? We're looking for the largest set of computers that are all connected to each other. So if they're all connected to each other, that means there can only be a group of 13, right? Or rather, there can be a group of 14. Sorry. The 13 outgoing edges, and all of those have to be connected. It says a connection. It doesn't say an immediate connection, but that does mean that there has to be some kind of way back. So the question then is what? Is there some kind of insight that can get us? I guess my question is, how many connections do there need to be for this to be a connected set of computers? Is it like one neighbors or like two neighbors or something like that? Can we even do what we are trying to think of doing? Let's get rid of that too high value. Let's get rid of graph dot stuff. And I guess let's get rid of part 1. So we have groups of 13 effectively, and they all have to be connected to each other, right? So I think it can only be one. We know these are all 13. So let's get rid of the code here and back it out and do this again. We don't really want count here. Well, actually I do want count here. I want to see if this is even, well, first of all, if it even runs. It looks like it does very quickly. And it runs very quickly now that I think about it, because this is the part 1 answer. We don't need starts with T here anymore. So if we open that up and we just do contains edges, then we get 11,011. Really? Let's do take 5, collect into a vec, and let's just start debugging our output here instead of returning it as our value. So we end up with 333, right? Let's do not last. Let's do max by lengths. Is max by not gonna work on this? Into iter option. Oh, right. Collect is no longer. And then what's the issue with max by? Expected closure that takes 2 distinct arguments. Yeah, okay. Some things are tuples, other things are not tuples. So this only gets us arrays of 3 nodes. Right. That makes sense. So neighbors, tuple combinations, right? But I guess instead of tuple combinations, this node is going to be, I guess, dot all, right? If they all contain an edge, then this is g.neighbors. I feel like because they all have 13, it can be a maximum of 14 nodes in the group for our LAN party, because otherwise it's everything as far as I can tell, right? Like if we take a look at this, I think everything in this graph is connected. This is one graph, as far as I can tell anyway. It is a little bit hard to tell. And we could do a strongly connected components on this just to check, since we do have it in PECgraph. I just don't exactly know what they mean by connected to each other. So let's do that actually, because otherwise we're just going to be guessing. And we've already done this. So let's do connected came from one of the days. So we did this on day 10. One of the reasons it's useful to do things like this on earlier days where they're not necessarily needed is because later days sometimes build on earlier days. And if you use the more advanced big crate things or whatever approach you want to build up on earlier days, then you do get the opportunity to reuse some of that. So strongly connected components from day 10 is actually from pathfinding for us, which is really interesting because what are we doing? Strongly connected components from, I didn't pull this whole thing in. Let's just grab this and let's stick this up here. And like, who needs graphs? So this would allow us to do this on every individual node to check the strongly connected components. If these are, pathfinding is fine, right? But what is I thought we did connected components already for our PECgraph. I guess we didn't, but this would be easy for us to check with PECgraph since we already have a graph. Maybe we looked at PECgraph that one day and decided to go pathfinding instead. I don't know why I had the idea that we had already done that. Let's comment out this max by 2. And of course the output. Connected 1. We have one big graph. We know that for sure now. So by connected, they have to mean directly connected, right? So it kind of has to be some play on this. And this is g.node. So for some node, right, we get all the neighbors, we get all the tuple combinations of those neighbors. We check to make sure that they all have a graph between, or like an edge between themselves. And if so, then we want to create this, right? So we don't need to flat map this. We just need a vec of node, right? So we get the node, we chain neighbor's node in. I don't know what's wrong with that. Will give me a second and I'll check it out. We want this to be a vec. Why is this an issue? It is an issue because chain and iters, and does this need to be like into iter to match the types up? It does, absolutely. So theoretically, we could get this. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 nodes that we then need to, we did sort them already, right? So it's what, output dot join comma is the password dot into it. Why is that an issue? Because output is a maybe. I think that's because output is an option, not a maybe. Maybe is a different language. So theoretically, this, did we give it a try? Do we just, pop it in here and not the right answer? Okay. So it's not just the node that has all of the other nodes connected to it, but we were able to find that, which is interesting. So do we do another loop and just try to expand this and expand this again and then expand this again? Like this ran really quickly. We could theoretically expand this. Maybe we don't want the max. Maybe we have more than that. Let's try it, right? And then we debug our output here, and we do. Really? All of them? How many are there? Did I mess up my check? 520. You know what? I'm not checking it. I am not checking this at all. Let's do why did I do that? Filter map. This is a Boolean. If this, then we do that. Else, none. I did not actually have working code. Okay, now we have 0. So we have no node for which all of its connections are connected. For each node, we can get all of the neighbors, right? And for each of those, we can get the neighbors of those. I wonder if we can do a heuristic where we kind of test to see how many neighbors for the neighbor match, right? So instead of doing this like we're doing here, we do, here are all of our neighbors, tuple combinations for all the neighbors, right? But not tuple combinations, rather, right? Like g.neighbors for this node. And let's to do this for a second. G.neighbors for this node, right? And for each of those neighbors, we want to run neighbors again. And then we can kind of like hash set and check how many connections they share. That doesn't really get us the answer. What if we graph a graph of second order neighbors? What does that look like? I think we can do that for each of them, right? Because the graph is, or the dot output is kind of, I don't know how to say that. This has 3, this goes into that, this goes into that, this goes into this all the way over here. Is there some issue with all the T's? Are all the T's connected? Are all the T's the root nodes? No, I think that's a Z down there. Does it spell out a word? I still very much wish that I knew what they meant by connected. I assume they mean like directly connected, at which point we could just go over decreasing numbers of neighbors, right? So we have our node, our root node, and we have it's everything included. Yeah, we have the root node, we have all the neighbors. Some subset of those neighbors are going to be connected to each other, and that is our group. So if we do g.neighbors, then we can run the program a couple times, right? But we have 13 neighbors is the wrong number. So what do we do? Dot combinations 12, you know? And then like dot map over that, which is going to be like an array now, which we are going to have to go over and do this. So it's going to be like r.iter.tuple. We don't want to really, tuple combinations, right? Tuple combinations, because we do need to check these edges. And it does need to be all. So it's going to be the same thing we did before. And it's going to be the same check we did before, right? Like if this, then we take this array, right? We add node to it. So r.iter, right? Or into iter or whatever we want to do here. And that's all of our nodes. We sort the nodes. This gives us a vec of possibilities, which I think we can just directly return. I'm going to make it easy on myself and just collect this into another vec. This is not a filter map anymore. This is just a vec, right? I think we actually don't have any issues with returning the iterator here, so we can map. And then this wants to do unique, so maybe we go back to flat map. And we have an issue over there. That's probably a move issue, which is fine. And then like we do this and we get a length of 2. A length of 2 is interesting. Let's see what those are. None and this thing. So just to be clear, 13 gives us none. 12 gives us an answer. Is this a sorted answer? Also, why do we get none and then some? That feels weird, right? I guess we're just mapping here. So we could filter map. And then we're flat mapping over node, g.neighbors for that node, combinations 12, filter map. We get all the tuple combinations for that combination of nodes. If that works out, then we get that node plus all the other ones, and we return that for some nodes. This happens for all of the possibilities of combinations for neighbors. This happens for every node, and we end up getting 1. So can we do something lower and hope we get some other values? Yeah, so we can get more values, but this seems to be the value, right? So if we do, I guess, if output dot, what is the right way to do this? This could do anything the way we've written it. We just know we want one output. So like if output dot length equals 1, output dot flatten dot join comma, return okay this, else panic, no answer, or 0 or many answers, I guess. And then we can just like debug output here, I guess. Output here should be that. So this is our answer. Is this sorted? Okay, sorted alphabetically, name of every computer, sorted alphabetically, A, B, C, D. I hope that's sorted. That looks sorted. That is the right answer? Hell yeah. That's the first one I'm really happy to have solved, actually. So let's take a look at what we actually did here. Because, we kind of took some liberties today, I guess you could say. Basically, the idea here is, and we don't need pathfinding there. So the idea here is we have some graph, right? And there is some set of nodes that are connected to each other strongly. Like they're all connected to each other, is what I mean by that. So to find that, we can basically get that node, right? Or get every node in the graph, of which there are like 4,000. So we don't want to use a super expensive algorithm or anything like that to find cycles. I think finding the largest cycle would have found this. Actually, that's not true. because they're all directly connected and cycles don't need to be. So wouldn't have been a cycle, actually, now that I think about it. But we can go for every node, right? And for every node, this number is kind of random. We are just working our way down from 13, which is the amount of edges that every node in the graph has, which we confirmed earlier by checking that for every node by doing just g.neighbors.count. So because 13 is that edge number, we tried 13 first because it was the easiest thing to try. Now, that didn't produce a result for us, so we're just bumping down to 12 and seeing if that produces a result. If 12 didn't, I would have gone down to 11, to 10, to 9. And if we got down to like 1 or 0, or even probably 3, I would have thought something was very, very wrong with this approach. Basically, we take all the neighbors, we take all combinations of 12 of the neighbors, because there are 13, and we run a filter map on that iterator, basically. Right? All of the combinations of 12 of the neighbors. We take that array, so this is our subset of neighbors. Let's call this like neighbor subset. Maybe that's a little bit easier to read. If the neighbor subset tuple combinations with itself, so for every pair of neighbors in that subset, they all contain an edge to every other neighbor, then we add node chained with neighbor subset, collect that into a vec, sort it because that's what we need to actually do for the password, and we return it. If they all aren't connected, then we return none. And for us, flat mapping this, what is effectively like a vec here, flattens that structure. We unique all of the potential combinations that we get, just in case. I think if we didn't have unique here and we ran this, we would actually get a whole bunch of results. But if you look at the sorting here, all of these results are actually the same. So we should probably have 12, 13 entries here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we do have 13 entries here. We have an entry for every node in this strongly connected cluster, because the way that we're doing this is we're iterating without any heuristic over every single node in the graph to find this. And we are not finding the first one, we're finding all of them. So we do end up doing this calculation 13 times, but we also don't know if 12 is the right answer. So we do have to unique here. That is very important because we are doing all of that extra calculation, and that's it. So because we used this graph structure, it was very nice to be able to use like g.neighbors, right? And we used itertool, so we like g.neighbors.combinations instead of needing to juggle a bunch of things. And then when we needed pairs of them in combination, we used tuple combinations. And when we needed to test, we did .all. So iterators really won out for us today. And this is not any slower than our part 1. Again, our solutions today aren't particularly speedy, but 2 milliseconds is fine for me for Advent of Code. So yeah, we used PetGraph, we did that. We end up with a nested structure anyway. I haven't thought through why that is. I think we get for each node, flat map, neighbors, combinations, right? This produces a vec of vecs. We filter map over that vec. Inside of here, we end up with a vec that we're returning. So we return a vec. This returns a vec. This is an iterator. So this flattens here and then nests the results of the filter map. So I don't know that our actual answer can avoid nesting here, because we actually do. Remember when we run this unique, for example, we actually do end up with the correct structure, right? We end up with basically a vec of those results. It just happens to be that we are looking at getting a single one. So when we know there's only one result, then we can flatten there. We could also do 0.join here. Maybe that's more readable to people. And if we get anything else, we panic and we just dump the debug. So that's it for today. I am reasonably happy with this. This was, I feel like, kind of nice in terms of implementation. I enjoyed the implementation. I could very much see this being a huge, rough one if you didn't kind of do the input investigation. I'm not a huge fan of input investigation problems, but at least it was clear, I feel like. Well, I somewhat feel like it was clear that there did need to be input investigation here. I don't know what I would have done if some of my guesses or, didn't work out. If they didn't, for example, just show 13 edges for all of the nodes, if they didn't show one connected component, and if they didn't, I think I made a set of educated guesses based on having seen Advent of Code problems like this in the past. I don't love that for the problem because I feel like newcomers will have a hard time with this, but I did have fun using PetGraph and visualizing some stuff and taking a look at things. So that's it for me for today. I hope you had a great day 22, I guess it is now, and I'll see you in the next one.